There's a photograph that has never been taken, not because no camera is good enough and not because no rocket is powerful enough to leave Earth behind. Humanity has parked machines in orbit around Mercury, skimmed the clouds of Jupiter, and photographed the icy face of Pluto from 4 billion miles away. No spacecraft has ever hovered directly above the sun's north or south pole and simply looked down. No camera built by human hands has ever captured our own star the way it captures every other planet. It is not a distance problem, it is an angle problem. Stay with me, because the reason is stranger and far more expensive than the sun itself. If you're new here, this is where we take apart real missions and real physics, no filler. So if that sounds like your kind of channel, the subscribe button is sitting right there. Let us go back to the beginning. To understand why looking down at the sun's poles is almost the hardest thing in the entire solar system to do, you first have to understand what launching a spacecraft actually does to it, physically, the moment it leaves the ground. Every planet, every asteroid, every spacecraft ever launched from Earth starts out sharing one enormous invisible inheritance. Earth's own orbital motion around the sun, a sideways velocity of about 30 kilometers per second, or roughly 67,000 miles per hour. That number is not a detail. That number is the entire problem. When engineers send a probe to Mars, to Jupiter, even out to Pluto, they are working with that inherited sideways motion, not against it. They simply add more speed in roughly the same direction Earth is already moving, the same flat plane every planet in the solar system orbits within, called the ecliptic. Reaching another planet, even a distant one, is fundamentally a question of going farther out or farther in, along a plane you're already moving through. It just takes patience, precise timing, and enough fuel to escape Earth's gravity. That's genuinely hard engineering. It is not, however, the hardest kind. Getting above or below the sun's poles requires something completely different. Not more speed along the plane. Everyone already moves in, but a change of plane entirely, canceling out most of that 30 kilometers per second sideways inheritance and redirecting the spacecraft's motion practically perpendicular to it. In orbital mechanics, this is called a plane change maneuver, and it is, kilogram for kilogram, one of the most fuel-hungry things you can ask a spacecraft to do. Doubling your distance from the sun might cost a spacecraft a few kilometers per second of extra velocity. Tilting your orbital plane by even a modest angle can cost more raw energy than escaping the solar system outright, because you're not adding to your existing motion, you're fighting directly against it. No chemical rocket ever built, launched directly from Earth, has enough propellant on board to make that turn in one shot. This isn't a straw man of old engineering. It was, and still is, simply true, confirmed independently by mission designers on both sides of the Atlantic decades apart. The number to remember going forward is 30 kilometers per second. That's the sideways motion every mission ever aimed at the sun's poles has had to somehow cancel out, and it's why, until 1980, no one had ever managed to do it at all. Consider what easy, by comparison, actually looks like. New Horizons launched toward Pluto on January 19, 2006, leaving Earth at roughly 26 kilometers per second, the fastest launch velocity of any spacecraft in history at that point, and it did that almost entirely by pointing itself outward along the same plane Earth already travels. Through, then letting a single Jupiter flyby in 2007 add even more forward speed rather than bend its path sideways. 9.5 years later, on July 14, 2015, it swept past Pluto at roughly 31,000 miles per hour, having traveled more than 3 billion miles without ever needing to fight its own inherited motion. That is what makes reaching a distant world achievable. Stack enough velocity in a direction you're already moving, wait, and let the calendar do the rest. Voyager 1 and Voyager 2 did something similar decades earlier, chaining together gravity assists at Jupiter, Saturn, Uranus, and Neptune, but the first, and for 35 years, only mission to actually solve this problem was a joint NASA-European Space Agency spacecraft named Ulysses, and the specific number scientists needed to hit was an orbital inclination of about 80 degrees relative to the ecliptic, essentially standing the spacecraft's orbit almost straight up on its side. Direct launch could not do it. Instead, mission planners used a trick that sounds almost like cheating. Send the spacecraft to Jupiter first, let the giant planet's gravity do the plane-changing work no rocket could afford, and only then head back toward the sun on a completely new trajectory. Read that again. The fastest way to fly over the sun's poles turned out to be flying away from the sun entirely, out past the orbit of Mars and Earth and everything familiar, all the way to Jupiter, 5 times farther from the sun than we are, just to borrow its gravity for a single, decisive turn. Here's where it gets worse before it gets better, because Jupiter's gravity assist came with a brutal side effect nobody could avoid. To reach Jupiter fast enough to make the maneuver work within a human working lifetime, Ulysses had to fly out through the coldest, dimmest part of the outer solar system's neighborhood, too far from the sun for ordinary solar panels to generate meaningful power. Every other deep space mission of that era at least had the fallback of getting closer to a planet or a star for sunlight. Ulysses, by the shape of its own trajectory, could never rely on that. The mission needed a nuclear power source instead, a radioisotope thermoelectric generator, converting the heat of decaying plutonium directly into electricity, entirely independent of sunlight. That decision alone would very nearly cost the mission its existence years before it ever reached Jupiter, but we'll come back to that. On February 8th, 1992, Ulysses passed within about 235,000 miles of Jupiter, close enough for the planet's immense gravitational field to bend the spacecraft's path by roughly 80 degrees, flipping it almost entirely out of the ecliptic plane and onto a track that would at last carry it over the sun's poles. 2.5 years later, in September 1994, Ulysses became the first human-made object to fly over the sun's south pole. It crossed back over the solar equator in early 1995, then passed over the North Pole that same year. Sit with that for a second. A journey that started by flying away from the sun, past Jupiter and back again, nearly 4.5 years just to get into position, before a single instrument could look directly down on either pole for the first time in the history of our species. What Ulysses found up there rewrote assumptions scientists had held for decades. The solar wind at high latitudes didn't keep, accelerating the way models predicted, instead leveling off at about 750 kilometers per second, nearly 1.7 million miles per hour, though not the runaway acceleration researchers had expected. And cosmic ray levels near the poles were noticeably lower than forecast. Because magnetic turbulence, the sun itself was generating scattered incoming radiation before it could concentrate there. This is not a footnote about one obscure spacecraft. This is the only direct, in situ evidence humanity has ever collected about how our star actually behaves at the one angle every other observation on Earth is structurally incapable of seeing. Translate that solar wind number to something you can actually hold on to. 750 kilometers per second is fast enough to cross the entire continental United States in about 5 seconds. A stream of charged particles pouring outward from the sun's poles continuously, every hour of every day, whether or not any instrument happens to be pointed at it. And Ulysses didn't just measure that speed once and move on. Because its orbit kept carrying it back around the sun every 6 years, it passed over the poles again in 2000 and 2001, this time during a period of maximum solar activity rather than the quiet minimum of its first pass, and then once more in 2007 and 2008, catching a solar minimum with the sun's magnetic polarity fully reversed from what it had measured over a decade earlier. 3 separate visits, 3 different phases of the solar cycle, 1 spacecraft. No other mission, before or since, has ever repeated that observation. Here is where this stops being an abstract question of orbital mechanics and becomes something that matters to every person standing on this planet right now. The sun's magnetic field, generated deep inside it and threading outward through the solar wind, is the primary driver of space weather. The solar flares and coronal mass ejections capable of knocking out satellites, disrupting GPS, and in extreme cases, threatening power grids across entire continents. Almost everything we know about how that magnetic engine actually works comes from watching the sun edge on. From within its own equatorial plane, the same limited vantage point every telescope on Earth has always been stuck with. Trying to understand a planet's engine by only ever looking at it sideways, never from above, is not a small handicap. It is the reason forecasting a major solar storm days in advance rather than hours remains one of the genuine unsolved problems of modern space science, and the poles are exactly where the missing half of that picture lives. Every satellite currently carrying your phone's GPS signal, every airline route planned near the poles, every power grid operator watching for the next major geomagnetic storm is ultimately downstream of a magnetic engine we have only ever examined from the side. Getting Ulysses into position to gather that missing half nearly didn't happen at all, and the reason has nothing to do with orbital mechanics. On January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 astronauts aboard and grounding NASA's entire shuttle fleet for the next 2.5 years. Ulysses had been scheduled to launch from the shuttle just months later, in May 1986. That plan collapsed instantly. But the deeper problem wasn't simply finding Ulysses a new ride, it was what Ulysses was carrying. Because the spacecraft's Jupiter-first trajectory ruled out solar power, Ulysses depended entirely on a radioisotope thermoelectric generator, loaded with plutonium-238, and in the raw, unfiltered aftermath of Challenger, the idea of ever again strapping nuclear material onto a vehicle capable of exploding on the launch pad became a matter of genuine public alarm. In March 1986, barely 5 weeks after the disaster, government officials were called before 2 House subcommittees to answer a single, uncomfortable question. Could a pad explosion crack open Ulysses's plutonium canister and scatter radioactive material into the atmosphere? The numbers presented were close enough to be frightening on their own. Engineers estimated a Challenger scale on-pad explosion could generate roughly 2,000 pounds per square inch of pressure, while the RTG casing itself was rated to survive up to 2,200 pounds per square inch. A 200 psi margin, on paper, standing between a contained mission and a public health emergency, debated on the floor of Congress. What followed was not a quick fix. NASA and its independent safety reviewers spent the better part of 4 years re-examining every engineering assumption behind the Ulysses and Galileo missions, redesigning the upper stage rocket combination that would eventually fling Ulysses toward Jupiter, and defending the mission against real, organized public opposition from anti-nuclear advocates who argued, not unreasonably given the moment, that no risk assessment written before Challenger could be trusted after it. Scientists who had waited a decade for a chance to see the sun's poles now had to wait through congressional hearings, redesigned trajectories, and a shuttle fleet slowly rebuilding public trust flight by flight, with no guarantee the mission would ever fly at all. The redesign wasn't only political, it was mechanical. Before Challenger, Ulysses had been slated to use one upper stage configuration to get from the shuttle's cargo bay onto its Jupiter-bound trajectory. After the accident, NASA and ESA reworked that combination into what became, at the time, the most energetic solid-fuel upper stage ever flown from an American launch vehicle, a two-stage combination that had to fire with almost no margin for error to send a spacecraft on the fastest trajectory any human-made object had yet achieved. Every one of those redesign choices had to be recertified from scratch, re-argued in front of the same safety panels that had just watched a shuttle disintegrate on live television. It finally did. On October 6, 1990, Ulysses lifted off aboard Space Shuttle Discovery, carrying the same plutonium-fueled generator that had triggered 4 years of hearings and redesign, and within about 7.5 hours, it was released into a trajectory faster than anything the Voyager or Pioneer probes had achieved at that point in their own missions, the fastest object any human had launched at the time, heading not toward the sun, but away from it, toward Jupiter, to finally make the turn nobody could afford to make directly. Its escape velocity, about 15.4 kilometers per second, briefly made Ulysses the fastest human-made object ever to leave Earth, a record it would hold only until New Horizons broke it 16 years later, on its way to a planet Ulysses would never visit, moving in a direction Ulysses had no need to go. Here is what is happening right now in 2026, 36 years after Ulysses first proved a polar solar orbit was even possible. Because Ulysses itself is long gone, its mission formally ended in 2009 after its plutonium-powered heaters could no longer keep its systems from freezing, and no spacecraft has attempted anything close to its 80-degree inclination since. The mission currently doing the most direct work on this exact problem is the European Space Agency's Solar Orbiter, launched February 10, 2020, and it is solving the plane change problem with patience rather than brute force. Instead of one dramatic gravity assist at Jupiter, Solar Orbiter is using a slow, repeated series of flybys of Venus, a smaller, closer planet, but one it can return to again and again, nudging its orbital inclination upward, step by careful step. Following a Venus flyby in February 2025, Solar Orbiter's orbit tilted to 17 degrees above the solar equator, and on March 23, 2025, its extreme ultraviolet imager captured something no telescope in history had ever produced, a direct image of the sun's south pole, glowing in ultraviolet light, its magnetic field visibly tangled and disordered, rather than neatly organized the way simplified models had long assumed. Meanwhile, a second NASA mission, Parker Solar Probe, has been chasing an entirely different record in the same neighborhood, flying repeatedly through the sun's outer atmosphere itself, matching its own distance record of roughly 3.8 million miles from the solar surface and its own speed record of about 430,000 miles per hour on close approaches through 2025. Astonishing numbers, but ones that come with an important asterisk. Parker's orbit stays close to the ecliptic plane. It gets extraordinarily near the sun in distance, but it has never significantly changed its angle. Getting even that close required its own extraordinary engineering. A carbon composite heat shield just a few inches thick, angled to keep Parker's instruments near room temperature, while the shield's sun-facing surface endures temperatures approaching 1,700 degrees Fahrenheit at closest approach. Proximity and altitude are two completely different achievements, and right now in 2026, only Solar Orbiter is actively climbing toward the second one. That climb has an exact date already locked into its trajectory, set by the unforgiving mathematics of orbital mechanics rather than anyone's press schedule. On December 24, 2026, Solar Orbiter will make its next close pass by Venus, using the planet's gravity to push its orbital inclination from 17 degrees to 24 degrees above the solar equator, a date ESA itself has marked as the formal start of the mission's high latitude phase. the point at which its view of the sun's polar regions becomes dramatically more direct than anything captured so far. It does not end there. A further Venus flyby is scheduled for March 2028, pushing the inclination higher still, and on June 10, 2029, one final gravity assist will carry Solar Orbiter to its ultimate operational tilt, 33 degrees above the solar equator, the steepest, most direct view of either pole any spacecraft is currently scheduled to achieve. Every one of those dates already exists in the spacecraft's programmed trajectory, set in motion the moment it launched in 2020. Barring a catastrophic failure, the countdown to the clearest images of the sun's poles humanity has ever produced is already running, with or without anyone watching. Now, the part that doesn't resolve neatly, because it genuinely hasn't resolved in the scientific literature yet, even with Ulysses' pioneering flybys and Solar Orbiter's new images already in hand, scientists still do not agree on the precise mechanism that generates and reverses the sun's magnetic field roughly every 11 years, a process broadly called the solar dynamo. One leading framework, often described as flux transport dynamo theory, argues that slow conveyor belt-like plasma currents physically carry magnetic field material from the equator to the poles and back down into the sun's interior, resetting the cycle. A competing framework points instead to smaller-scale turbulent magnetic activity distributed throughout the sun's convective layers, arguing the large-scale cycle emerges from the statistical behavior of countless smaller local processes rather than one grand conveyor belt. What most people are not seeing when headlines describe new images of the sun's poles is that a picture, however unprecedented, is not automatically an explanation. Solar Orbiter's own 2025 South Pole images showed a magnetic field far messier and less organized than either leading model fully predicted, and researchers studying that data were clear that reconciling it with either theory, or building something new entirely, remains ongoing, unresolved work. Step back from the spacecraft and the plasma physics for a moment, and a larger pattern comes into focus. Humanity reached Pluto, 4 billion miles away, essentially by being patient and moving in the same direction the whole solar system already moves, extending an existing motion rather than fighting it. Reaching the sun's poles, sitting comparatively next door in cosmic terms, required something almost the opposite, not going farther, but turning, fighting against the very inheritance every object launched from Earth carries with it. It is a strange, almost poetic asymmetry. The star that lights every clock on the planet, that every civilization in human history has watched rise and set, remains from directly above, essentially unseen, not because it is too far, but because reaching it from that angle asks more of our engineering than reaching almost anywhere else in the solar system. Progress here didn't come from brute forcing more thrust. It came from a decades-long willingness to travel the long way around, out to Jupiter and back, or through repeated patient nudges past Venus, because sometimes the shortest path in distance is the most expensive path in physics, and the only way through is sideways. Notice, too, how differently the two solutions to the same problem were built. Ulysses solved it in one enormous irreversible gesture. A single Jupiter flyby, a single 80-degree turn, an all-or-nothing maneuver that had to work perfectly the first time, or not at all. Solar Orbiter is solving the identical problem through the opposite philosophy. Small, repeated corrections, each Venus flyby, buying only a few more degrees of tilt, spread out over the better part of a decade. Neither approach is more correct than the other. They are simply two different answers to the same unforgiving arithmetic, separated by 30 years of accumulated spacecraft engineering, propulsion efficiency, and mission design confidence. And what connects them is the same stubborn refusal to accept that a problem is unsolvable just because the direct path is closed. There's a detail from Ulysses' own final years worth sitting with. By 2008, the same plutonium generator that had triggered 4 years of congressional hearings, public protest, and redesigned rocket stages before the mission ever left the ground was finally running out of heat. Not out of function, out of warmth. The spacecraft's own instruments, its own fuel lines, its own internal wiring, began creeping toward temperatures they were never built to survive. Not because anything had broken, but because the radioactive core that had carried Ulysses past Jupiter, over both solar poles, and back around twice more, simply could not keep giving forever. Engineers on Earth spent its final months carefully rationing what little heat remained, prioritizing the components most likely to keep the spacecraft alive. A few more weeks, the way you might close off unused rooms in a house to keep the ones that matter warm. On June 30th, 2009, after nearly 19 years, almost 4 times its planned lifetime, Ulysses finally went cold and silent, the only spacecraft that has ever looked directly down on both of the sun's poles, its last transmissions arriving from an angle no telescope on Earth had ever occupied, and none has occupied since. Somewhere out beyond Jupiter's orbit right now, Ulysses is still moving, still tracing the wide, tilted ellipse its one great gravity-assisted turn carved out in 1992, silent and unpowered, A dead machine still faithfully following the only orbit in the solar system built specifically to look down on a star that can no longer see it back. So here's everything in one breath. Reaching distant worlds like Pluto is physically a question of extending motion. Humanity already inherits from Earth's own orbit, while reaching the sun's poles requires canceling that 30 kilometers per second inheritance entirely. A plane change maneuver so fuel expensive no rocket has ever managed it directly. Ulysses solved that problem in 1990 by flying out to Jupiter first, borrowing its gravity for an 80-degree turn, nearly derailed years earlier by the Challenger disaster and the public safety fight over its plutonium power source, before finally passing over both solar poles between 1994 and 1995 and rewriting assumptions about the solar wind and cosmic rays. Today, Solar Orbiter is climbing toward that same vantage point gradually, through repeated Venus flybys, already delivering the first ever images of the sun's south pole in 2025, with its inclination locked to rise again this December and reach its final 33-degree tilt in 2029. And the actual engine driving the sun's magnetic field in its 11-year cycle, the thing all of this effort is ultimately trying to see, remains, even now, a genuinely open scientific question. If you want to see what Solar Orbiter actually captures when it crosses 24 degrees this December, subscribe and turn notifications on, because I'll be covering it the moment the images come back. Here's the question I'm actually curious about. If you had to choose, would you rather see the first fully mapped image of the sun's pole or the first confirmed answer to what's actually driving its 11-year cycle underneath? This is a genuine either-or, not a rhetorical one. The two answers would tell scientists very different things about our own star. Drop your answer in the comments. I read every single one.